If it is there, I can't help it. So because I need to finish the portions right now. So welcome Wing Commander Rao. So
Thank you, Dr. Narayan. Thank you so much.
Yeah. So last class we had on 20th November 2020. Then you had a huge break for your placement training. I hope you had a wonderful placement training. All of you are placement ready. So this subject is little tricky. So we need to just relook what we have done earlier. So I'll just recap what we have done. Retarded current in the last class. This is part B of your module 4. So that is where we are. Part B of your module 4. Part A of your module 4, we have done point sources, arrays of point sources, then radiation pattern of 2 point sources, n point sources, maxima, minima, radiation pattern plotting, all this we have done. So this is part B. We'll be doing about derivation of short electric dipole and all. So in that, the first concept is retarded current. Students, please interrupt me if you are not understanding or if you are having difficulty in understanding. Since we are meeting after a long time, our frequencies to once again match, it will take some time. So we all know, can you all see the screen?
Yes, sir.
Yes, sir.
Okay. So retarded current is defined, first before that, what is the time varying current? I is equal to I naught cos omega t, which implies instantaneous propagation effect of the current. For retarded current, retarded means retarded in time. So retarded current, you have an additional term here, R by C, which you can see here. If I put I within the bracket, it implies retarded current. Retarded means it is retarded in time. So an event which happens prior to the present will be reflected in the present. So this square bracket implies retarded currency. For example, you have a this is going to be reality very soon. Definitely in your lifetime, you are going to have an like airplane travel from here to USA. You will have airplane travel from here to a moon, if not Mars. Already you have Elon Musk planning a SpaceX program wherein the super rich of the world can afford and go into outer space and come back. Suppose you go to moon and you want to talk to your beloved ones in the back to earth. If you call them using mobile phone, definitely you tell hello. It will take some few seconds for the receiver to receive as hello. Then once again he tells you back hello. Again you have to wait. So this is going to be the scenario in future. That time you tell hello. The moment I receive hello, there may be some 7 to 10 seconds delay. So that is what I am telling you as retarded. That is a retarded voice in this case, because the retarded current is because the signal at the receiving end at the earth will take some time. I hope all of you got what I am trying to tell. Any doubts? Veena, did you get what I am trying to tell?
Yes, sir. No doubts.
Oh, yeah. Okay. Okay. Wing Commander Rao, my voice is clear, right?
Yeah, your voice is absolutely clear.
Okay, loud and clear, fine. So that is your equation 2. So the equation 2 implies that the disturbance at a time t at a distance r from the element is carried by a current, retarded current I. So movement I put I within a bracket, from today we'll call that as retarded. Retarded means current is retarded. It is not mental retardation. Don't think it is some negative word here. This is current retardation or voltage retardation. Please keep that in mind. That occurred at an earlier time t minus r by c, where r by c is the time interval required for the disturbance to travel at a distance r in the free space at a velocity c is equal to 300 meters per second. Velocity of light is your 300 meters per second. So this is the maximum speed at which it can travel. So t minus r by c, that is your occurred at an earlier time. So that is caused due to the current that has occurred at an earlier time, t minus r by c. So this is what we understood in the previous class. Now we'll be understanding one concept. First you have to understand what is short dipole. So I'll just write here, today is 1st January 2021 and I'm starting, what I'm starting is SHORT, short dipole. If you have notebook, please take down If you write with me, it is better. Okay. So what is a short dipole? We'll draw now. By the way, any New Year celebrations or Robert? Till I explain short electric dipole. You seem to have gone to a restaurant yesterday.
No, sir, not yesterday.
Okay, some other day you went. See, I keep seeing your social media profiles, no Instagram and all. I just like that asked. It's good to enjoy, but nothing wrong you have done. Don't worry.
They will not tell, even though they are going, they will not tell. Don't worry, guys. You can enjoy. There is nothing to, nothing is stopping you to from enjoy. Okay, you must enjoy. In fact,
Okay. So, Beena, what did you do?
No way, sir. At home only we all were
Okay, very
partying.
good. Very sober celebrations. Okay. You won't know, my son, who is just 5 year old, he was celebrating more than what we were celebrating. So, he was more excited about the new year. See, I'm trying to draw it to the best of my ability here in the online platform. So, please bear with me. This is your transmission line. Okay. This is your dipole element, and this thickness is D. Thickness of the wire, that is D. This is your length of the dipole L. See, both sides it is equidistant. I could not draw it exactly, so please excuse me. So both are equidistant. Now I think, I hope it is equidistant. Okay. 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 Have you drawn that? All of your drawing or not?
Yes, sir.
Okay, please draw. It will be good practice before the examination. Kavya UP, are you there? Simran Saxena, are you there? Okay. Tanupriya, how are you?
Yes, sir, I'm fine.
Any New Year celebrations?
Yes, sir, we just got a cake yesterday and then we
Okay,
parted.
very good. At least people are celebrating. See, we always can't be serious. Even we should have lighter moments.
Yes, sir.
Fine. Have you drawn this? Finish drawing, everyone.
Yes, sir.
Okay, please write down a dipole antenna is a system consisting of consisting of two straight conductors having two straight conductors having total length L very much less than lambda. Very much less than lambda. What is lambda? Your wavelength. Okay. Is it clear? Any linear antenna may be regarded as composed of large number of short dipoles connected in series. Okay. Assumption. Length is far lesser than wavelength and thickness of your dipole D is far lesser than length, far lesser than your length L, where L is equal to length of the dipole, D is the thickness, lambda is the wavelength. Okay. Right now, the above figure, consists of simple thin conductor of length L, very small l, with a uniform current I and point charge Q at the ends. Okay. Have you written?
Yes, sir.
Now, please take down this figure. Can you all see the figure?
Yes, sir.
Please take down this figure. This is a short electric dipole. I'm placing in a spherical coordinate system where you have components ER, E theta, and E phi. That's all is this figure. Nothing to get worried about. Okay. If you can't take down the figure later, you take down because I need to complete something. This more than this figure, the figure below is more important. Now you please take down. That is the brief introduction about short electric dipole. This is field of a short dipole. Okay, now this is very important for your examination point of view. They will tell derive an expression for electric field due to a short electric dipole. So instead of a short electric dipole, I will tell due to a fields due to a short electric dipole. Fields due to short electric dipole. Clear? Clear, everyone? Okay.
Yes, sir.
This topic is very important. So let us do this fields due to short electric dipole. Now you please draw this figure, which is slightly more important than the figure on top. That is the three-dimensional figure. Even if you don't draw, that is fine. This particular figure which I am trying to draw is more important right now. Approximately this is at the center. All of you are able to see?
Yes, sir.
Who is that answering?
Good morning, sir. I'm Mahima, sir.
Okay, thank you, Mahima. Beena, are you able to see?
Yes, sir. Yes, sir.
Please be alive on the this one, ba. See, if I was taking the offline classes, my interaction will be far better. Because of the shortage of time and other things, I'm trying to do it very fast. I will generally take slightly more time than what I'm taking right now. This is your point O. This is your length of the dipole L. This is your elementary length dz. This is your elementary length dz, this point. Okay. This is your distance r to a distant point P. This is your point S1. Sorry, distance S1. This is your distance S, and this is your distance S2. Okay. Now what we are trying to find is, you are trying to find the electric field at this distance point P due to this dipole of length L. So that dipole I have just put as a one rectangle shape here to represent, and I have taken an elementary length dz. From this elementary length dz, the distance to point P is S. From the other end of the dipole, the distance is S1, and from this end it is S2, and from the midpoint it is a distance R. I hope it is clear. Is it clear?
Yes, sir.
Yes, sir.
Okay. So if this is the origin midpoint, what will be the upper length, Purvachandra Prakash? From this point to this point, what will be the length?
L/2.
Very good. So I should write here as L/2. Okay. Mr. Saurabh, but can you tell me this the distance now? Down one.
It will also be inverted.
No, no. What is the sign here? Minus or plus, sir?
Minus L/2.
Good. All of you seem to be on track. So all of you are clear with this?
Yes, sir.
Yes, sir.
Fine. Write down. We know that current I is equal to I naught. What is current I? Just now I have done that.
I naught cos t minus.
Okay, I naught you can do cos or e raised the power j omega t. Is this clear? Is this right?
Yes, sir.
So okay. Now, what will be the retarded current I? Mahima, can you try it? Purva Chandra, you only tell. What I should write here? I naught.
E power j
Ah,
j omega t minus
very
r by
good. T.
minus r by c.
Excellent. Outstanding. You will get S grade in antenna. My best wishes for that. Purva Chandra, you will get S grade in antenna. My best wishes for that.
Thank you, sir.
Write down. Where I is the retarded current. Okay. Next. Omega r by c, that is this omega into r by c, is known as phase retardation. Phase retardation and is given by 2 pi f r by c. Omega is your 2 pi f, so r by c is r by c. This many radians, this many radians. Clear?
Yes, sir.
Yes, sir.
Please draw one more diagram before we proceed. This should be exactly at the midpoint, this pencil mark what I am doing. All these are parallel lines, okay? Clear? In your drawing.
Yes, sir.
Yes, sir.
Are you all able to follow what I am doing? All these are diagrams, okay? There is nothing
Yes, sir.
to break your head on this. What is this distance? R. Okay, from your midpoint O. That is what we have seen in this diagram. Same thing I'm trying to replicate here. So this is your distance S1 and this is your distance S2. Okay. So I have to draw here one more line. This distance, this will be L by 2. This will be minus L by 2. This distance, now this distance, I'll use some other color, will be nothing but your L by 2 cos theta. Okay. Clear?
Yes, sir.
Okay. This angle is your theta. That will be L by 2 cos theta. Similarly, this also will be your L by 2 cos theta. Okay. Quickly write down the vector potential at point P. So your point P is somewhere here where all these lines are reaching. So vector magnetic, all this in field theory you have learnt if you remember. Vector magnetic potential at point P due to elemental length dz, due to the elemental length dz is given by your vector magnetic potential Az is equal to mu by 4 pi. Okay, we have to give this equation number, so this is okay. Mu upon 4 pi integration minus L by 2 to L by 2 minus L by 2 to L by 2 retarded current I divided by distance S dz. Call this as equation number 3. This is your definition of your vector magnetic potential. Vector magnetic, okay. Fine. Now, write down, we know that okay. Okay, we know that retarded current I is equal to I naught e raised to the power j omega t minus S by C. S by C where? This, if you are taking this elemental length dz, what is this distance from here to point P? What is this distance, sir? Okay, we'll call this as figure 1. So you have to refer to figure 1. What is the distance between elemental length dz to point P?
Yes.
That is why I have put here S. Yes, that is why you have elemental length dz coming here. So that distance is S. So you will have retarded current I is equal to I naught e raised to the power j omega t minus S by C. Fine. So now if you integrate your equation number 3, what you will end up getting is your vector magnetic potential Az will be nothing but mu naught by 4 pi. Retarded current I will take it outside. Integration of minus L by 2 to L by 2, 1 minus of S dz. Agreed? Yes or no?
Yes,
Yes,
sir.
sir.
Fine. So if I have to integrate this, what happens, Purva Chandra? Mu naught into retarded current I divided by 4 pi. So if I have to integrate this, what happens? This will be Z limit minus L by 2 to L by 2. Am I right?
Yes, sir.
Okay, very good. So till here we have come. So substitute this value of okay. After integrating, if you apply the limit, what happens? L by 2 minus of minus L by 2. What happens? L, no?
Yes, sir.
Okay. Am I right or wrong?
L by 2 minus of minus L by 2. So it's L.
So you will have L, right?
Yes, sir.
Okay. So this your vector magnetic potential Az. Please counter check the derivations what I am doing, at least these portions. So this will be mu naught into retarded current I divided by 4 pi. So this will be L by 2 minus of minus L by 2, that is L by 2 plus L by 2, that is L. So this S should come outside. Literally, I forgotten this. So this should be here. Okay. Yes or no? Have you all forgotten this? Yes. Okay. So this what happens is this is for elemental length. This one. So for in a general case, this S should be written as what? What should be written instead of S? This is for a elemental length. For a general case, what will be the value of S? R. Clear? So all these assumptions you have to do. Then only you will arrive at that equation. So this will be a R. 4 pi R. Okay. For a general case, write down. For a general case, S is equal to R. Okay. So this will be mu naught into retarded current I L divided by 4 pi R. This is your vector magnetic potential Az. So this can be rewritten as mu naught L I naught e raised to the power j omega T minus R by C divided by 4 pi R. Okay, call this as equation number 4. Clear up to here?
Yes, sir.
Okay. Please write one sentence here. If the distance from the center of dipole is very large compared to length, that is R is far greater than length L, and its wavelength lambda is far greater than length, then approximately distance S is approximately equal to distance R, neglecting the phase difference of the field contribution from different parts of the dipole. Okay, so your equation Az is nothing but mu naught into L I naught divided by 4 pi r e raised to the power j omega t minus r by c. This is your equation number 4. Okay. We know that, write down. We know that scalar potential V of charge distribution is given by scalar potential V. For scalar potential we write as V, and for vector potential we write as A. Got it? This is your vector potential and V is your scalar magnetic potential. 1 upon 4 pi epsilon line integration of scalar potential V. This is retarded charge density rho by S d tau. Call this as equation number 5. Where retarded rho is your retarded charge density. Mahima, are you with me?
Yes, sir.
Okay. Retarded charge density rho can be written as rho naught e raised to the power j omega t minus r by c. All this as equation number 6. D tau is a infinitely small volume element, and E naught is the permittivity of free space. E naught is the permittivity of free space. Okay. Now, in our case, we have only two charges there, one plus q on top, one minus q on bottom. There are not multiple charges. So since it is a dipole, okay, write down. Since the region of charge in case of dipole is confined to points at two ends of dipole, scalar magnetic potential reduces to 1 upon 4 pi epsilon. This will be plus q by S1. Please, I will see why it is S1. Please see the figure. This is where I place your charge plus q. This is where I place the charge minus q. So what is this distance? S2. This is your point P. Getting it?
Yes, sir.
This is your point P. So this is your charge minus q. So from the charge minus q to point P, distance is S2. And for charge plus q to point P, distance is S1. Is it clear?
Yes, sir.
Yeah.
So this is going to be retarded charge minus q by S2. This is your equation 7. Okay. This is your retarded charge where q is nothing but is the retarded charge. So your retarded charge q can be written as integration of I dt, retarded current I dt. So if it is only q, it will be integration of I dt. Since it is retarded charge q, it will be integration of square root of square bracket of I dt. So this can be written as I naught e raised to the power j omega t minus s by c. Anyway, we'll make it r by c, that is later d tau. So even if you write as r by c, this is not an issue. So this can be written as, if you integrate this will be I upon j omega. Write it like this, I upon j omega. Okay, so your okay, substitute equation 8 in 7. Substitute equation 8 in 7. So you will have retarded charge potential will be I naught divided by 4 pi epsilon j omega. So this will be I naught divided, this is, okay. So your retarded charge density, how I should write? Q I naught e raised to the power j omega t minus s by c divided by s1. So how will I write q1 plus q? I naught I have taken outside the bracket, so this will be e raised to the power j omega t minus s1 by c. Is it clear? Minus,
Yes, sir.
okay, e raised to the power j omega t minus s2 by c. All of you have to practice this, divided by s by 2 distance. This is your equation number 9. Okay. Now write, call this as figure 2, this figure as figure number 2. Just a second. I'll just see your syllabus 1 second. Your 17 scheme, right?
Yes, sir.
I just got some small doubt. Let me check the syllabus. Okay. See, this is what we are doing. Right now, we are doing introduction, short electric dipole introduction, fields of a short electric dipole, general and far field cases. Then we'll be doing radiation resistance of short dipole, thin linear antenna, radiation resistance of lambda by 2 dipole. So this I am doing now fields of a short electric dipole, general and far field cases. This is the exact topic what I am trying to do. That is not there in the notes which is given. That's why I was just counter checking whether that is there in the syllabus. I very much remember it is there in the syllabus. You got it what I am trying to do right now?
Yes, sir.
Okay. So this is what I'm trying to do. Fields of a short electric dipole. Whenever I do a syllabus, comma, full stop, and apostrophes, everything I try to finish. Nothing is left to chance. Okay, fine. Now coming back to this this one, write down referring to figure 2. Referring to figure 2. Okay. Referring to figure 2, the ends of the dipole. Referring to figure 2, the ends of dipole may be considered parallel to each other so that S1 is equal to R minus L by 2 cos theta and S2 is equal to R plus L by 2 cos theta. Call this as equation number 10 and call this as equation number 11. Okay. Now, one small thing you have to remember this far field components, because derivation from here will get very tough. So we'll do some assumption and give it, because this is what your BTU wants. Substitute equation 10 and 11 into equation 9. Okay. After some mathematical operations, it may be shown that the fields of a short electric dipole ER is equal to I naught L cos theta divided by 2 pi epsilon naught e raised to the power j omega t minus r by c into 1 upon cr square plus 1 upon rho omega r cube. What is this equation number 12? Next, E theta is equal to I naught L sin theta e raised to the power j omega t minus r by c divided by 4 pi epsilon naught j omega by c square r plus 1 upon cr square plus 1 upon j omega r cube. Sorry, this is j, not rho. What is this equation number?
2.
Very good. Right, H5 is equal to I naught L sin theta e raised to the power j omega t minus r by c divided by 4 pi into j omega by cr plus 1 upon r square. This is your equation 14. The far field components are given by the far field components are E theta is equal to j I naught beta L divided by 4 pi epsilon naught CR sin theta j omega. Sorry. Don't worry, seeing this equation, I'll tell you how to remember this. E raised to the power j omega t minus r by c and h phi is equal to j I naught beta L divided by 4 pi sin theta e raised to the power j omega t minus r by c. This will be your equation number 15 and your equation number 16. See here, fields of a short electric dipole, general case and far field analysis. This is your far field analysis and these three equations are your general case. Okay, now please see the equation. I'll just see how many of you are still available. Okay, around 60 people are there. Just see this equation. I naught L divided into cos theta divided by 2 pi epsilon e raised to the power j omega t minus r by c. If you see e raised to the power j omega t minus r by c is one common factor throughout. This is your component er, e theta and h phi. Can you see this diagram here? Er, e theta. Here h phi is not available, so er, e theta, e phi is there. So we are deriving here er, e theta and h phi components of the fields of the short electric dipole. So er component is I naught L cos theta divided by 2 pi epsilon e raised to the power j omega t minus r by c 1 upon cr square plus 1 upon jr cube. So E theta is equal to I naught L sin naught e raised to the power j omega t minus c. Here 4 pi epsilon will come instead of 2 pi epsilon. J omega c square r plus 1 upon cr square plus this whole term will get coming here as it is. Cr square j omega r cube. H phi is I naught L sin theta e raised to the power j omega t minus r by c 4 pi. Here epsilon is not there. Here one c will be less j omega by cr plus 1 upon r square. Here far field components are very important. You have to remember them. I naught j into I naught beta L divided by 4 pi epsilon cr sin theta e raised to the power j omega t minus r by c and h phi is j into I naught beta L 4 pi sin theta e raised to the power j omega t minus r by c. Okay, you need to practice them. So from here the derivation is not here optional. So there directly I have written down the equation. So this general case and far field components case you have to remember. So finally you need to write this 5 equations. Is it clear?
Yes, sir.
Okay. I'll just tell you the significance of the field component. Before that, please write down E theta by h phi is equal to square root of mu naught by epsilon naught. This is equal to 377 ohms. This is also equal to intrinsic impedance Z naught and is given intrinsic impedance Z naught. That much if you write, it's more than sufficient. Okay. So what is the significance of field components? Is one small thing. Significance of field components. H of phi. See here H of phi. It varies with, see the general case, it varies with the square of the distance r. Okay, it inversely varies with the your distance r. This term is called the radiation component, and it basically represents the radiation of the electromagnetic field, electromagnetic wave from the conductor. So this H5 component is inversely proportional to R and is called as what? Radiation component. Okay, clear?
Yes, sir.
Okay. Sorry. It varies. This component you have to consider. It varies with the distance r, not square of the distance r. This is known as your radiation component. Next one, the term which varies square of the distance r is called the induction component. So the which one varies square of the distance r. This varies square with the distance r is known as your induction component. Induction component of the field. Which is that induction component?
The second one.
Yeah.
First one.
Not exactly the second one, this first one. Can you see the first component you have to consider? This is your CR square. So that is your induction component. The term which varies square of the distance R is called the induction component. And when that, okay. So the what is the significance of ER is when the distance R is very small, the induction term is dominating. And when the distance R is very large, your induction term is negligible. Now, what it happens is this induction component will, when R is very small, this component will be very large. When R is very large, ER will be very small. Is it clear? Correct or not?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So, if R is very small, induction component is very large, and vice versa. So, and vice versa. So if your induction component is very large, what happens? You don't radiate power. So if your distance R is very small from the antenna, your point P is very small distance from the antenna, then you cannot radiate any power. Is it clear? This is the derivation for that. If the distance R is very small from the antenna, you can't radiate any power. That is a very important finding from this equation. Is it clear?
Yes, sir.
Okay. Okay. Next, the component E theta has both induction and radiating field. Okay. Along with the component which varies with the cube of the distance r, and this component is okay. Along with the component which varies with the cube of distance r. This is called as electrostatic field. This is called as electrostatic field or simply electric field. Okay. Now, in your VTU question, starting from the electric and the magnetic field vector, magnetic field potential, obtain the far field components of a short dipole. 12 marks question. Electric and magnetic field of a short dipole. 10 marks question. Derive an expression for radiation resistance. Okay, the radiation resistance is our next topic. Now, I will just tell you the significance of field component for the people who did not understand one more time. Now you have here basically 5 equations here: ER, E theta, H phi, and E theta and H phi. You may be wondering why ER is not there in the far field components. Can anyone justify why ER is not there in the far field component? Anyone? You understood my question, right?
Yes, sir.
Okay. Why ER is not available in the far field component? Only two there: E theta, H phi. Why no ER?
Sir, ER is inversely proportional to square of the distance, sir. So if R is very small, then radiation, we cannot radiate any power, sir.
No. Far field means what, Ma? You are very close to the answer. What is far field? What is the meaning of far field, Mahima? The distance R is quite far from that point P is quite far from the dipole. That means what? R will be very large.
Yes, sir.
If R is very large, what happens to ER?
Negligible.
If R is very large, what happens to ER?
Negligible value.
It becomes negligibly small. So in far field, you will not have ER component. If you have ER component, it is not an antenna, because it is an induction field. It is not a radiating field. Which is the radiating field here? H phi. H phi component is inversely proportional to the square of this, inversely proportional to R. That is your radiation field component. ER component is your induction field component, because it is varying square of R. So if R is very large, what happens? ER becomes very small. If R is very small, ER becomes very large. Induction field means it will not radiate power. So if your R is very, if your point P is very close to the antenna, no signal you will get. Is it clear?
Yes, sir.
Okay. Yeah, H phi is your radiation field component. E theta has everything. Radiation field, R component, R square component, also R cube component. You have 3 components coming into E theta, and somehow it will also come in the far field, because it has all the 3 components, and its existence also comes in the far field. So in far field, you will have only E theta and H phi components. You will not have ER component. These questions are going to ask you in the third internal test. These twisted questions. If you attend the class, you will be able to answer. Otherwise, you will get one big anda. Is it clear? Okay.
Yes, sir.
So you want me to go through the derivation once again before concluding for the day?
Yes, sir.
Okay. Today we understood what is a short dipole. Short dipole is nothing but a dipole with a plus q and minus q placed at the 2 lengths of a thin linear antenna. The thickness of the antenna is far lesser than the length, and the length is far lesser than the wavelength. So this is the assumption which we have taken. So this dipole we are placing in the spherical coordinate, and we are finding E theta, ER, H phi, and E theta. So these are the components we are trying to find. That is nothing but fields of a short electric dipole, or fields due to a short electric dipole. For that, we are we are deriving this equation, wherein we have taken the length of the dipole plus q and minus q placed at the 2 ends, origin taken at the center, at the origin O. So you will have length L by 2 and minus L by 2 on 2 sides. You take elemental length dz, which makes an angle theta with respect to S, which is the line which is connecting the elemental length to the distant point P. So you have to find the electric field at the this distant point T from the dipole antenna. So it makes a distance r from the center of the dipole and the distance s1 to the upper end of the dipole and the distance s2 to the lower end of the dipole. We know that I is equal to I naught e raised to the power j omega t, and retarded current I is equal to I naught e raised to the power j omega t minus r by c, where r by c is nothing, omega r by c is nothing but the phase retardation. So as I explained you, plus q and minus q charges you are placing on the two ends of the dipole. Then we are defining two major things here: vector magnetic potential and the scalar potential. Vector magnetic potential Az is nothing but mu upon 4 pi minus L by 2 to L by 2 integration of I by S dz. That is the definition of vector magnetic potential. So your retarded current I, you substitute, integrate that. Instead of S, substitute R for a general case. After integration, you get this equation 4. Then after you get this equation 4, we define scalar magnetic potential V as 1 upon 4 pi epsilon integration of scalar magnetic line integration of retarded charge density rho by S d tau, where rho is the retarded charge density and d tau is the infinitely small volume element. E naught is the permittivity of the space. Since the region of charge in the case of dipole is confined to the 2 points at the two ends of the dipole, we have plus q and minus q that we are defining. This is also retarded charge. So retarded charge is the q is nothing but integration of I dt. Retarded charge q is equal to integration of retarded current I dt. Retarded current I expanded I naught e raised to the power j omega t minus s by c. That is nothing but I naught divided by j omega after integration. Substitute in equation 7, you get like this. Then S1 is R minus L by 2 cos theta and S2 is R plus L by 2 cos theta. Up to equation 11 you come, substitute 10 and 11 into equation 9, and after some mathematical manipulation and lot of mathematical steps which go on to pages which I have not done here, you get three components. So in the general case, ER, E theta, H phi, which you are required to remember. One is proportional to the square of distance R, one is proportional to the distance R, one is proportional to all three. So ER is nothing but your induction field component. E theta is your component which has everything, and H phi is your radiation field component. The far field components are only E theta and H phi. So the what to say? The ratio of E theta by H phi is given by square of mu naught by epsilon naught, nothing but 377 ohms is equal to Z naught. So this is where we end today. So anything you would like to ask me? Yes, anything you would like to ask me? Yes, Mahima, anything?
So no, so we understood the concept, sir, today.
It is somewhat tough. You need to practice a lot. Otherwise, this will not come. Okay, you simply listen to my lectures also, it will not come. If you don't listen to my lecture, definitely it will not come. So those who are absent today, I cannot help it because I need to cover your syllabus. That's why I'm going at supersonic speed to cover your syllabus. And I find that many people are absent today. I'm very highly disappointed with that. Okay, that is a different story altogether. So this is the conclusion for today. So I cannot help for the people who are absent.